Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're looking at elimination reactions of alcohols. Last lecture, we finished off looking at substitution reactions. We looked at how you can make a halide in place or substitute a halide for an alcohol. And we learned that there was methodologies that allowed for the SN1, SN2, and even a new reaction mechanism we referred to as the SNI reaction mechanism. If we want to carry out an elimination reaction of an alcohol, the alcohol must be reacted, as in the substitution reaction, with a powerful acid. Usually, you use acids of the type such as concentrated H2SO4, which may or may not be dissolved in water, or concentrated H3PO4. So concentrated sulfuric, which may be diluted somewhat, or concentrated phosphoric acid. The product of the elimination reaction is an alkene. Plus, we end up removing H2O. Because we lose H2O, the reaction is sometimes referred to as a dehydration reaction. Now, the ease of dehydration follows the typical elimination rates that we have observed for E1 and E2 reaction mechanisms. In both mechanisms, tertiary reacted faster than secondary. Now, in the case of which reacted faster than primary, methyl's not really involved because methyl cannot form an alkene. You need two carbons to form a double bond. Now, the tertiary is faster than secondary in the E1 because of carbocation formation. The more substituted carbocation is more stable due to inductive electron donation. In the case of tertiary being faster than secondary for E2, this is related to the stability of the alkene. More substituted alkene double bonds are more stable. Since the transition state had some double bond character, and since tertiary always yields a more substituted alkene than secondary, the transition state is more stabilized when it has more substituents on it. As a result, tertiary is faster for E2. Now, in terms of mechanism, tertiary and secondary go E1. Primary goes E2. Now, primaries go E2 simply because the energy of the carbocation is too high. The carbocation is so unsubstituted, so high energy, that the E1 pathway is effectively shut off. But this is an interesting change. You see, in alkyl halides, the predominant reaction mechanism was E2 only, tertiary, secondary, primary. And the reason for that, in the case of alkyl halides, was that effectively we were in fairly non-polar solvents. The most polar solvent that you could have was a water-alcohol mixture in the case of alkyl halide chemistry. Now, in the case of alcohols, however, our solvent is concentrated acid. Concentrated acid represents one of the most polar environments that you can generate. As a result, the E1 becomes favored. Do you remember your favored by statements for SN1 and E1? Well, in the case of E1, it's weaker bases, higher temperatures, and polar product solvents. Well, there's nothing more polar product than a powerful acid. As a result, the E1 mechanism is accelerated in the case of alcohols. And it's favored so much so that tertiary and secondary can go E1. All right. Why don't we take an example of the E1 mechanism? And I'm going to begin with step 1. Step 1 of an E1 mechanism, as always for an alcohol, involves protonation. Protonation. So we'll take a look here. So a typical E1 mechanism here. E1 mech. And let's try 3,3-dimethyl-2-butanol. So here's 3,3-dimethyl-2-butanol, and we hit it with acid in our first protonation step. And this results in protonation of the alcohol and production of the oxonium ion. The purpose of this, remember, is to generate a good leaving group. If it left as OH, that would be if this OH left, it would leave as a hydroxide, a powerful base. That's a poor leaving group. When it's been protonated, it will leave as water. Water is a weaker base, better leaving group. So step 1, protonation still happens. Okay. Step 2, is ionization. And ionization is sometimes referred to as carbocation formation. And in this case, since H2O is being kicked out, the mechanistic step is sometimes called loss of water. In either case, the most important feature is actually the formation of the carbocation. So we have the oxonium ion, Salome pair, minus H2O, the water leaves, and we form our carbocation. Okay. Step 3. Now you notice step 2 and 3 here in alkyl halides are step 1 and 2. And the reason is we had that initial first step. The first step, protonation, isn't really part of the SN1. It only happens when necessary to make a good leaving group. And it will happen in any reaction mechanism where you require a good leaving group if necessary. Step 3, of course, is rearrangement. You must always, whenever you say E1 or SN1, you must draw your carbocation on scrap paper, take a close look at it, and see if rearrangement is possible. Now, I look at this carbocation. I ask myself what kind of carbocation it is. The carbon with the positive charge has 2 carbons attached to it, so it's secondary. I can carry out a 1,2 methyl shift. That is, shift this methyl group over. I'll get this. And a positive. Now, if I look at the carbon bearing the positive charge, now it has 3 carbons attached to it, so it's tertiary. And I examine, there is no resonance stabilization of the secondary, therefore the tertiary is indeed more stable. So tertiary is more stable than secondary. This shift does happen. Step 4 is base attack. Now the first thing we have to consider is, hey, we're an acid. The reagent was concentrated acid. What kind of base is available to actually act the role of base and remove a proton? Well, I guess the question is to ask, let's say you're using H2SO4, and it's pure H2SO4. What happens to H2SO4 when it loses a proton? Because step 1 had H plus attack, so presumably an H2SO4 lost a proton. So who is around after that proton's removed? Well, the answer to that, of course, I'm going to use B for base. Okay. B colon, how's that? Equals. Well, if we lose a proton for H2SO4, we get HSO4 minus. So the base could be HSO4 minus. Secondly, if you actually dissolve your H2SO4, so it's a fairly concentrated acid, but it is dissolved in water, you could have some H2O around. H2O is also a weak base and may grab a proton. So our base is either H2SO4 or H2O. Okay, so I'm going to put B with a lone pair here. It may be charged, may not be charged. Now, to make a double bond, we have to remove two atoms off of two neighboring carbons so that we can form the pi bond between them. We've already lost the alcohol group where the positive charge is. That means we only have to pull off an H on a beta carbon. Now, in order to do this, I must find out the beta carbons. The carbon with the positive charge is my alpha carbon. Carbons attached to the alpha carbon are beta. So this carbon's beta, this carbon's beta, and this carbon's beta. Now the beta I put in the square box. If I pull an H off of either of those betas, I will generate the same alkene. You should try doing it. Make a double bond by pulling an H off the CH3 pointing up, and then make a double bond by pulling the pulling H off the CH3 to the left, and try naming that molecule. And you'll find you have the same alkene. So two alkenes result. If I pull an H off the beta that's not in the square box, I get this guy. And if I pull an H off one of the betas in the square box, so one of those methyls, this one, I get this alkene. Now, utilizing the Zaitsev rule, which states that the most major product is the more stable alkene, I can determine which alkene is major. The most stable alkene, of course, is the more substituted double bond. So I localize the double bond. There's a double bond, and this guy has 4 substituents off the double bond, 4 methyls. If I localize the double bond here, that's not a plus. I don't want that to look like a plus. This double bond has 2 substituents, an isopropyl and a methyl. A double bond with 4 substituents is more stable than a double bond with 2 substituents. Now, when the more stable is major, that's Zaitsev elimination. And Zaitsev elimination happens all the time in this course, except for the one example you were given in alkyl halides of Hoffman elimination. So, indeed, this guy is major. And this one's minor. Okay. So there you have elimination E1 for an alcohol. Well, what about E2 elimination? Well, typically E2 reactions occur slowly and compete with SN2 reactions. They are not hugely important for alcohols. And I'll give you an example which we will revisit in a moment. Consider ethanol. Ethanol is a primary alcohol. We're going to look at inorganic esters shortly, and we're going to learn that ethanol in sulfuric acid actually at low temperatures produces inorganic esters. At 140 degrees Celsius, you get SN2 happening and you produce diethyl ether. Elimination can be made to occur, but you really have to hit it with heat. To get E2 elimination, so here is my, shall we say, drawing of my H's. So I've got this in a staggered conformation. I've got my OH anti-periplanar to this H. So my HSO4 minus, if you like, so this guy gets protonated. My HSO4 minus will come on the protonated alcohol acting as base, and I'll attack that proton. These two electrons will go here, and water will leave. And so I'll get ethene plus H2O. You have to heat this system to approaching 180 degrees to 190 degrees, 189, something like that, degrees C, which means a lot of heat. At typical lower temperatures, the E2 mechanism just isn't available. The alkene that forms is not substituted and is a less stable alkene. Hence, to form, you have to put a lot of heat into the system. Okay. Now, one last point that I want to make about product alkenes is that when you form alkenes, and we'll see this more closely when we look at alkene chemistry later on, transalkenes are typically more stable than cis. And the reason for this is pretty simple. It's due to steric repulsion of the large groups. Now, R represents alkyl groups, and the alkyl groups being methyls or ethyls typically are bigger than hydrogens. And you get more repulsion here between these large groups than when they're on opposite sides. So typically trans is more stable than cis. Due to this repulsion, which is, of course, a steric effect. So there's a little extra tidbit that we're going to be covering later on. All right, what if we examine a different type of elimination? What if I attempt an elimination reaction on a 1,2 diol? Rather than just having a single OH, this molecule has two OHs. this molecule has an IUPAC name of 2,3-dimethyl. Butane two, three, diol. Its common name is Pinacol. Pinacol. Well, if I want to do elimination on a 1,2 diol, and notice I call it 1,2, you say it's a 2,3 diol. When we use the term 1,2, we're not using IUPAC numbering. When we say 1,2, we're meaning that neighboring carbons, that the alcohol groups are attached to neighboring carbons. If you didn't know how long the chain was, you would just simply say 1 and 2 to indicate neighboring carbons. So yes, while an IUPAC is a 2,3 diol, when we say 1,2 diol, we're simply meaning that somewhere along the chain there are two carbons next door to each other that have OHs. Okay, well, in order to do this reaction, if it's an elimination, we have to get a good leaving group. So step 1 of the elimination in the Pinacol case is protonation. Okay, so we hit this with H2SO4, our H plus will come in and protonate. Now, first thing to note is you're not going to protonate both alcohols. That would produce a dication, and due to repulsion, the concentration of dication would be very small compared to the concentration of the monocation. So in other words, the most prevalent species that's protonated will be the one that protonates only one of the alcohols. And of course, that can happen. We'll get an oxonium ion, no problem there. Lone pair on the oxygen, positive charge now. Make this a little longer. Alcohol that's not protonated. And our next step, as usual, is ionization or you may call it carbocation formation. Step 2, ionization, carbocation formation. So we have an H, an O, an H, positive charge, attached to a C who has a couple CH3s. Loses water, and we get carbocation. as carbocation. Now, what's step 3? Step 3 is check for rearrangement. Now, you might be jumping ahead and saying, I'm intuitively bright. This is a tertiary. There's obviously no resonance, so I'm going to say this is more stable, and I'm not going to draw it. And just move on to step 4. Be careful. Always draw out the carbocation, even if you think that it's the most stable. So step 3. is rearrangement. And take a close look. Try shifting, see what you get. So here we are. We have a C with a positive. Off of that C is a CH3. We have a C. With an OH. And let's look. Take a close look. Let's try a 1,2 methyl shift. If I do a 1,2 methyl shift, I'd get something like this. Okay. Again, the carbon with positive charge has 3 carbons attached to it. This guy's tertiary. Carbon here has 2 carbons attached to it. It is secondary. Tertiary is more stable than secondary, so this shift should not happen. But this is where you have to look carefully. The only time a secondary becomes more stable than a tertiary is if there's resonance stabilization. If I dump in this lone pair here, I can actually draw a resonance structure. With a positive charge. It's on oxygen. And you might say, wait, oxygen's electronegative. That's unfavorable. Positive charge should not be on oxygen. Look carefully and remember your resonance rules. Who is the greatest contributor and why? The upper contributor has 6 electrons around carbon. The bottom contributor has 8 electrons around every atom. The most paramount rule in drawing resonance contributors is that filled octet structures are greater contributors than those structures that don't have filled octets. The bottom structure is the major contributor. Okay. Step 4, the final step, is deprotonation. Removal of a hydrogen to generate our alkene. Except, in this case, deprotonation does not form an alkene. So our base, let's say, is HSO4 minus again. It could be, I'm going to put B. I'll put B colon may equal HSO4 minus, or it may equal H2O. We don't know what. It'll go grab the H. And if that happens, I'll get this. I get this molecule. Elimination. An elimination reaction that did not yield an alkene. We made a ketone. The molecule, IUPAC name, is 3,3-dimethyl butane 2 running out of room on 3,3-dimethyl butane 2-one. Its common name is Pinacol. When you try to do an elimination reaction on a 1,2 diol, that is two OH groups on carbons adjacent to each other. Because 1,2 shifting yields this resonance stabilized alcohol, and the O reforms the double bond in making the most stable contributor. The product is not an alkene, but a ketone. This mechanism is known as the Pinacol Rearrangement. Oh man, write that again. The Pinacol Rearrangement. And it is an important elimination mechanism that you need to know. Of course, remember that rearrangement always occurs faster than alkene or ketone formation because it's an intramolecular reaction. All right? Okay. What we want to talk about next is the acidity of alcohols. If I consider water, for example, water can react with itself. And water, when it reacts with itself, is in equilibrium with its protonated version and its deprotonated version. Now, at 25 degrees, the concentration of water is 55 moles per liter. The concentration of these two components can be determined, and they are both at 1.00. times 10 to minus 7 molar. Now, Ka has 55 molar built into it, and so it removes one of the waters from the calculation. We've looked at that. So if I actually wanted to determine the equilibrium constant, I could take 1.00 times 10 to the minus 7 moles per liter square it and divide it by the concentration of the reagents. Now remember what Ka is. You may have to look back. Equilibrium constant would have been 1 times 10 to the minus 7 squared over 55 squared. But water, where it's a solvent, is a constant, and that's multiplied out. So Ka has one of the waters built into it. And so on the bottom, you just have 55. When you are done, you get Ka equals 1.82 times 10 to the minus 16. So the pKa of water, the equilibrium constant for the dissociation of water, equals the negative log of 1.82 times 10 to the minus 16, or 15.7. Now what does this tell you about the acidity of water? Large pKa's are indicative of weak acids. Low pKa values are stronger acids. HCl, strong acid, typically has pKa's less than 1. Okay, so many strong acids have less than 1. H2O is not a very strong acid. What about when you substitute carbon onto the oxygen in place of a hydrogen, like in methanol? Well, in pure form, the pKa, so let's write pure, the pKa for methanol is approximately 17, which suggests it's even a weaker acid. When you dissolve methanol in water and it's dilute, you get similar pKa's to that of water because it's primarily in water and the hydrogen bonding effect and behavior takes place in water. In water it's around 15.5, which is experimentally very close to that of just water. The point is, water and alcohol are weak acids. So if you deprotonate them and you make OH minus from water, or you make OCH3 minus from methanol, take a proton off, what are these guys? Well, they're relatively strong bases. And you already know that from your study of base strength and nucleophilicity. They're relatively strong bases. Okay, so a question arises then. If alkoxides are strong nucleophiles and strong bases, and we've already seen where we use these in alkyl halide section as strong nucleophiles, how can you prepare alkoxides? How can you prepare these alkoxides? Well, in order to deprotonate an alcohol, in order to deprotonate an alcohol, I have to react this guy with a strong base. And hydroxide is not powerful enough a base to drive it all the way. I need something stronger to form RO minus. So, who are the strong bases that we can use? For this reaction? Well, some typical strong bases are sodium hydride. Sodium hydride. Sodium hydride is sodium plus H minus. H minus, hydrogen, would have a lone pair, and hydrogen is not very electronegative at all. It's one of the least electronegative atoms. And so it doesn't like bearing a negative charge. So when hydrogen does have a negative charge, it is very basic. If we use hydrogen as our base here, it's going to grab a proton. And what does H plus H minus give? Well, of course, it's pretty obvious. You get H2 gas. Okay, so H minus is a powerful base, and so sodium hydride can be used. Another one is sodium amide. Sodium is plus, NH2 is negatively charged and has actually two lone pairs. Now NH2 is a deprotonated form of NH3. Now we said we couldn't use hydroxide, it wasn't strong enough. NH3 is a stronger base than hydroxide. By the time you deprotonate NH3 and get NH2 minus, you have a very powerful base. Pulling a proton off the alcohol will convert NH2 minus into NH3. Okay. What other strong bases can be used? Well, of course, there is the Grignard reagent. Remember Grignard reagents such as methyl, magnesium, bromide? Here, magnesium is less electronegative than carbon. Carbon's delta minus, magnesium's delta plus. Grignard produces what behaves as if it is a CH3 minus. Now, in fact, the carbon is closely associated with magnesium to help stabilize the C minus, but in reactions, Grignard reagent behaves as if it's alkyl minus. So if you had methyl Grignard, it's like methyl minus. Ethyl Grignard would be like ethyl minus. Carbon's not very electronegative, doesn't like a negative charge. If there was a methyl minus, it would be a super powerful base, and because of this, Grignard is a super powerful base. In fact, you learned that Grignard is such a powerful base that it would grab a proton before acting as a nucleophile. And so you're told your molecules can't have OH groups on them because the methyl minus would grab the H plus, and methyl minus plus H plus, what would that give you? That would give you CH4 gas, which would bubble the solution. So Grignard reagents, Grignard reagents, are powerful bases as well. Okay. What other bases can be used? We could use sodium metal or potassium metal. sodium metal or potassium metal. Okay, let's look at some reactions and see if we can figure out how this would occur. So if we start with, say, C2H5OH, we can hit this with 2 sodiums. If we do that, the 2 sodiums transfer electrons to the antibonding levels of the oxygen-hydrogen bond. So if I come down here and I look at the oxygen-hydrogen bond, if I were to break this bond homolytically, that is, 1 electron of the bond goes with each atom, I would get a radical on the oxygen and a radical on the hydrogen. Now, if sodium, and they would have been neutral, if sodium's added 2 more electrons to that bond in the antibonding levels, the oxygen would get 1 electron from 1 sodium, and the hydrogen would get 1 electron from the other sodium. That would put an extra electron in each one, so when it's split, the oxygen would be negative, and the H would be negative. And now the sodiums who lost the electrons would become sodium plus. So once this reaction is done, we get C2H5O minus and a sodium plus. And to that, we can add a sodium plus and an H minus, sodium hydride. Now, sodium hydride is a super powerful base, and if you are in ethanol as a solvent, it's not going to hang around and do nothing. The sodium hydride is going to react. It's going to grab the H plus, and we've already seen what happens. The H plus pulled off, of course, will make C2H5O minus and A plus. But H minus, when it grabs an H plus, becomes H2 gas. H2 gas. Now, if I add up these 2 reactions, I get 2 C2H5OH plus 2 sodiums plus NaH goes to 2C2H5 O minus Na plus, let's make it better, positive, plus H2 gas plus NaH. Now, what happens here? When you have 2 identical groups on either side of the equation, they cancel, just like in a mathematical equation. So the hydride and hydride cancel. We can remove it. And for simplicity's sake, I could divide this whole equation by 2. That would give me the equation I have in my handout notes, if you are following along. Ethanol plus sodium goes to C2H5O Na plus 1/2 H2 gas. Now this reaction works for any molecule. I could use tert-butyl alcohol. And the potassium metal does the exact same thing. So I could say tert-butyl alcohol plus potassium gives me potassium plus 1/2 H2 gas. Okay. What's important to note is why you get a half H2 gas. And you have to understand these first two steps, and you should be able to give them. The top two steps show how the reaction happens. So they are mechanistic description. They are a mechanism for the reaction, which gives the product. So if I ask for a mechanism of how this reaction, let's call them reaction 1 or reaction 2 take place, you would have to give me a description like the above description to explain where the H2 gas comes from. Now let's talk a little bit about nomenclature. How do you name the deprotonated alcohol? We already know how to name the alcohol. The common name for the alcohols are ethyl alcohol and tert-butyl alcohol. The name of the deprotonated version comes from the common name by dropping YL alcohol. So let's take a closer look at that, if we can. And let's write down his common name. Ethyl alcohol. Tert-butyl alcohol. All you do to the alcohol name is drop the YL and the alcohol and add oxide for oxygen. So ethyl alcohol becomes ethoxide. Ethoxide. And the Na, if it's there, if it was just C2H5O-, you'd say ethoxide. If you're given the counterion, you write it as a separate word up front, sodium. As a separate word. So what we have here is potassium tert-butoxide. We drop the YL and add oxide. And this applies for every alcohol. Okay, so there's the nomenclature and the preparation of the alkoxide. This is how we make the powerful nucleophiles that we used in the alkyl halide section of the course. Now, there's an alcohol I do want to look at because we have indicated that alcohols are weak acids. We have stated that because alcohols are such weak acids, you cannot use hydroxide to deprotonate them. Well, there is one alcohol. Remember this alcohol? What's its name? Phenol. This alcohol can be reacted. with hydroxide. And if you do so, it fully deprotonates. This alcohol fully deprotonates. Now, the question is, if hydroxide fully deprotonates, that means this alcohol is a stronger acid than most other alcohols, which hydroxide can't deprotonate. And the question is why? The answer is simple enough. It is resonance. The alcohol is resonance stabilized. And we can draw its resonance structures. And we get 5 resonance structures altogether. Five resonance structures. Now, why would this make the original alcohol more acidic than the regular alcohol? Why is phenol more acidic? Well, you recall that none of these resonance structures actually exist. What exists is the resonance hybrid. What exists is the resonance hybrid, where the negative charge is delocalized over all those positions. Now, when you take a negative charge and you delocalize it, that is, you spread the charge out over many atoms. You stabilize that charge. Stabilizing the charge results in a greater ease of formation. That means easier loss of H+, which means stronger acid. So typically, phenols are stronger acids because they are resonance stabilized. And if you use sodium hydroxide, you would make the sodium salt of phenol. What is the name of this anion? Well, if I use sodium hydroxide, I'd have the sodium salt. If I use potassium hydroxide, I'd have the potassium salt. The deprotonated ion is called phenoxide. I've also seen the name phenolate used, where they take phenol and add ATE for the negative charge. In this course, though, we will use phenoxide for the anion. Okay. Okay, there you have it. I'm Dr. Brian Lloyd. This is my Scribblecast.